square the wave function. And then if you want to get the actual probabilities of some particle being found in a certain volume, you then integrate that probability density over the volume you're talking about. So, given these, what's the probability? Now you're talking a central potential, right? That's this whole chapter, theme of this chapter. So, what's the probability then of finding, let's say, well, the electron? That's symbolized as E for electron, and a minus, like a superfix. The minus because that's its charge, negatively charged. So a positron, the antiparticle of an electron, would be symbolized, written as E and a plus here, where the minus is. So what's the probability of finding the electron at a distance r from the nucleus and r plus delta r? In other words, finding it in an onion shell of thickness dr, and the radius of the onion shell, so to speak, is r. Okay, so here's your probability density p, and dr, as simple as that. I think it does. Probably this is clearer this way. Okay, so you're talking about r, you're not interested in the angles, so yeah, theta and phi. So find a probability density here, which will depend on, oh, hold on. The text didn't go into this terribly clearly, but let's see. Why is there no m dependence? I need to think about that. Well, anyway, this is what the text is giving. So now this makes more sense to me, because that's an actual volume, right? Because this 4 pi r squared is the surface area of the sphere. The radius of this sphere is r. Think of the onion layer, the shell of the onion shell, onion layer. And if you divide that, multiply that area of the sphere, multiplied by like its thickness, dr. So that will give you a dV of volume. And this is your probability density. And where I have a question mark is why no angular dependence? Simply because you're interested in r, I guess. All right. Now here's some graphs for different cases for wave functions for given n and l. So here n is 1, and L angular momentum is 0, n is 2, angular momentum is 0, and so on. Yeah, so 1, 2, 3, 4, 5, 6 cases. And I think they're the same 6 here, right? The same 6. Is that true? Hold on, let me just check. 1, 0, 2, 0, 2, 1, yes. 3, 0, 3, 1. Not quite. Okay, we did not do a 3, 2, but here is like an extra one, right? Okay, well, with that question mark about why is there no spherical harmonic y in here? Why would that be? I think we talked about that just a few sessions ago. We have to average it out. Well, I still have a bit of a question mark about that. Okay, so I'm thinking real time here. Well, assuming that's the case, then you plug in these values, and you sort of see. I mean, this one's pretty trivial, right? So this is effectively just a constant, and this is your ball radius. So when E is nothing, so that just becomes 1. So, oh, this is starting here. Yeah, it's starting here at 1. Does that make sense? Yeah. So when R is 0, so this is 1. So you get this term. So I guess it starts at about 1. Right? At R. Actually, this is not just R. It's R divided by the bore radius. Okay. And why do you do that? Well, it's more convenient. And along the y-axis here, what do you have? So probability in dimensionless units. We talked a bit about dimensionless quantities in terms of L, M, and T. L for length, M for mass, T for time units. And defining it this way, dividing R by the bore radius, A0, you get dimensionless quantities. And so what? It's just more convenient. Then your quantities do not depend on which particular unit you chose. You're talking centimeters or miles, or right? You get rid of all that because it's dimensionless. It's just numbers, straight numbers. Okay. So here's what the probability density would look like, right? For this case, the first one, and for the second one, it gets a bit more complicated. Okay, and the third one here, why is that? Look, it looks a bit like a cosine, right? See, well, actually, it looks a bit more like a bell curve, but, the exponential. So this 2-1, this corresponds to this one. 3 here. Why this sort of wiggly stuff going on here? I guess due to this term, things get complicated. So, right, and eventually the exponential will kick in and kill it. Take it down to 0. Eventually, the exponential dominates what this is, and it's just from mathematics. 3-1. That's this one here. Slow. No, this one here. Well, see, you would need to draw these. Obviously, you'd need a computer, right? So it's not at all obvious what's going on here. So you just plot this squared, of course, and so you get this is sort of where the electrons are for the different energies and different angular momentum. Right? So in some places, like in this case, the electron just would not be at that particular distance, but quite a high probability to be at this distance, because the probability density is high. So you can see the electrons, they tend to congregate more at certain distances than others, right? And that's what this is showing. All right. Now next session, I'll mention what we've done so far is still pretty simplified, right? There are other phenomena going on in the hydrogen atom that certainly complicate things. So I'll mention a couple of those factors, but to analyze them in depth, well, we will to some extent in future chapters. Next chapter, for example. But some of the other factors, it's graduate level. It's tougher, especially when you get into quantum field theory, QFT. All right, so I'll finish there and mention some of these factors.